Hi everyone. So today we'll be solving the question from Stiver's SD sheet, that is search in a 2D matrix. And this question says that we are given a 2D matrix of m into n, and the following are the properties of the matrix. Each row is sorted in, this is the row, and this is sorted in non-decreasing order. The first integer of each row is greater than the last integer. That is, if this is the integer, then this is greater than the previous integer, that is 1. Definitely we can see 10 is greater than 1, and again 23 is greater than 10. So we are given a particular target, that is here it is 3. So we have to check whether the target is present inside this 2D matrix or not. Very simple. Here target is 13. You can see anywhere this inside this 2D matrix the target is not present. Therefore the we will return it false. Very simple. We can use for loops to iterate in the matrix and just check whether target is equals to if it is present or not in the matrix. If matrix is equals to target I or not, then that's how we can get one of the solution, right? Which will have big of n square and space will be big of 1. I'll show you my solution. This is a simple thing that comes to your mind, right? The for loop, basic, brute force approach. This one. So here I have taken, since it's a 2D matrix, therefore an and a matrix, initializing the row and the column. And then since it's a 2D matrix, therefore for two for loops here for the row and for the column. And then I'm checking whether the target is present in the matrix I or J or not. If it is present, then we will return 1, which is means true, and return 0, which is false. Return 0 means false and return 1 means true here. The time complexity is big of n square, and the space complexity here is big of 1, right? Very simple. Two for loops for row and column, and the space complexity is of course big of 1. No extra space, no extra space is used here. Since the time complexity here is very much, so what can, like, which space complexity, we don't have to worry for that. It's completely the optimized one. Now the worry part is for this big of n square. See, we are just searching the many like things here, right? We are searching elements here inside this matrix, 2D matrix. Therefore we can think that, like, something like search operation, right? We are basically doing search operation for anything searching. We have, what do you use, like linear search, binary search, different type of sorting operations. That's the thing that we use, right? Those are the thing that we use. So definitely you can think that the best approach while we do perform anything search operation, what comes to your mind? Definitely the binary search, if I'm not so wrong, which have a big of, I hope all of you know about the binary search. I'll just show you. So this is, you can always refer to GFG for reading the article. This helps a lot. Okay, what was the time complexity of big of n square? We are worried about the time complexity. The search time complexity for time complexity for binary search is big of n log n. So we are getting it less than n, like not, this is greater than, definitely big of n, right? Sorry. Again, this is also greater than, this is less than, like big of log n is the best. So we are getting that solution, which is definitely great, right? So let's look for this big of log n solution. Like, it's very simple. We are first, like, we are in the question, if we do anything search operation, at first show the brute force. After that, your mind should go to the binary search thing, which have a, which gives a time complexity of big of log n, right? This is the thing. How binary search work, if you see here once, we always take a mid. Okay, we take a, this is not the proper code for the binary search. I'll show you from here. Binary search code. Okay, pseudocode was here. So actually this is how binary search is taken. we take a low pointer, which basically the first, which points in the first index of the array, and then the high pointer is that which points to at the end of the array. And when we take middle, okay, which is basically between low plus high by 2. Definitely if the first and the last, then divide, if we divide it low plus high, like if we divide it by 2, that is of course the middle, right? And then till while L is less than high, we will do this thing that we will understand here. Okay, so I'll show you the binary search code. Very simple. I've taken n for row and m for column, and low and high pointers. Low is 0, which points at the first index of the matrix, and high points at the last index of the matrix. And then we have low less than n, it will run till it's less than n, and high should be greater than is equals to 0 or minus 1, anything you can take. And our car is basically matrix of low and high. This is a pointer, okay? This will point the low and high. And now if car is equals to target, okay, if we are getting the target, then we will return true, right? But if say car is basically the low and high, definitely, so if we are one go we are getting, definitely we will return true. But if target is more than the car, like the current pointer, then low plus plus. You know why? I'll tell you. If target is more than the car, that means target is somewhere here, okay? And if you see this, like in binary search, you will always remember that something related to descending order will definitely come. Why we will low plus plus? If target is more than, of course target will be somewhere here, because the elements present this side are smaller than here, definitely. So we will go one place ahead, okay? So what we will do, if we are searching for 7 here, then sorry, if we're searching for 7 here, then what's gonna happen? We are here. We are at 5 right now. It's more than the car, right? Target is more than the car. If we are at 7, at first we are, see, I'll say you are right. And for binary search, always remember that something will be given with like ascending or descending order. That's the catch. Here it's given that it's in uh, descending order, right? Increasing order. So that's how the binary search thing works. And now what you will see that if we are here at this index currently, so but target here is we have to find for 7. We are just finding 7. Just forget about 3. We are finding 7. Since target is more than 5, therefore of course the low pointer will come this side, because the low pointer is this side and the high pointer is this side. So low pointer be like, no, I'll come one place, since target is bigger. So therefore low plus plus. If it is opposite, if suppose we are finding for 1 and a high pointer says like, no, like target is smaller, so of course high pointer will be like, of course we are at here now. Of course 5 is smaller than 1. We are searching, this time we are searching for 1, right? So 5 is smaller than greater than 1. Therefore 1 will be this high pointer be like, no, yeah, I have to come forward, like high minus minus. That's why I've written high minus minus, and return, finally return 0. This is the simple thing. Return false if in none of the cases are true, because we are not at that time, at that case we are not finding any target value here. So the TC will be, we go of n log n, because there's a while loop also. And the time space complexity, all of you know, I'm not gonna write. It's of course big of constant space. I hope you understood the question. There was a bit of glitch in between, but yeah, forgive for that. And yeah, I hope you enjoyed. Keep lit coding. Bye.